if you just talk.
Hi, this is Adam Simcoe, and I'm talking about our ENG06 Final project for section A04. We chose the bacteria image processing task, and what we are doing is we are counting the amount of bacteria in specific image. It's a photomicrograph of stained bacteria in a blue color. So then this is the way we started doing it, and now here is one of our next team members starting off with task 1.
Hi, this is Natasha. So for task 1, what we started to do was first you want to clear all the variables and clear the command window, just so you start with a clean slate. We said P is our input of the image that we have the user specify. Then we save the image as the variable I, and as you can see, we switch it from color to black and white with this bit of code on lines 28 and 29. Now we have some who's displayed with asterisks in front of them, and what this does is you can, if you want to, you can delete the asterisks as well as the %, like such, just so you can see some extra information. Otherwise it clutters the command screen, so we chose to not include that. But if you want the extra information on the picture, you can add that in there.
Okay, our next task, we needed to display the overall image that was converted into black and white. So you can see we need to have several nested loops in this for error checking and many other processes within this project. So we just have our first variable labeled as z. And while z is equal to 1, it's displaying the image, the converted black and white image, with the name photomicrograph of bacteria stained with a dye, and then we have the number tile off, so it won't be labeled also as figure 1. It shows the reduced image that's in black and white here with this bit of code, and then we turn on the axes, and the origin in a MATLAB image is always at the top left corner, and the x-axis was shown at the bottom of our image. And although this was technically correct, it was a bit disconcerting to have the axes not lining up correctly. So with this bit of code here, axis location top, we move the x-axis to the top while the y-axis is still on the left. So the overall image just looks much nicer. We turn the grid on and then set the y scale to segments of 25, and then the y to also a scale of 25, so that the user can most easily choose a specific bacterium to use as an example for the rest of the process.
So for task 3, our main objective here was to prompt the user to select a bit of the picture in which there will be a isolated bacterium. So first, to show them that, we had this little bit of code right here, and it just pretty much tells them what we're trying to do, that they should be trying to isolate a bacteria that is approximately representative of any average bacteria in the picture. So we have some more loops here just for error checking. So we set EL1, which we abbreviated for error loop 1, equal to 1, and while it is equal to 1, we have the range x as the input of the minimum value in the x range. Now we added the isNumeric just to ensure that the value is in fact a numerical value, and if it is not, the program will ask the user to re-input the minimum value for x. We also included that the x minimum must be in between 0 and 313, which is the number of pixels in the x direction. Next we added another error loop, 2, and with the same idea that the range x2 would be the maximum value of x, and this also must be between range x1 and 313. If not, there will be a display that says entry invalid, and the user will be prompted to re-enter the maximum value of x. Now we're doing the same thing with the y values, setting 2 more error loops, error loop 3 here and error loop 4 down here. And it's the same exact idea as with the x values. We select range y1 to be the minimum y value inputted by the user, and it also goes through checking whether it's a numerical value and also if it is within the range specified. The same thing goes for range y2, which is the maximum y value. Again, it's making sure that it is a numerical value and is above the minimum value of y, but also below 300, which is the maximum amount of pixels in the y-axis. This last bit of code for task 3 pretty much just says that range x, it goes from the minimum value of x to the maximum value of x, and that range y, it goes from the minimum value of y to the maximum value of y.
And the next task, we show the image specifically specified by the user in the previous task when they were giving the minimum and the maximum values of the x and the y. It displays this isolated bacterium, the title, an isolated bacterium. And this image needs to show only one specific bacterium. All the black pixels in this image need to belong to only one bacterium that is representative of all of the rest of them as a whole. So we ask the user here with the one-back input, is the bacterium one complete displayed? Is only one complete bacteria displayed? Yes or no? And this is entered as a string, so the user does not have to put quotations around the input, y or n. If it is, in fact, one complete bacterium with no other black pixels on the image belonging to another bacterium, then it goes into a loop that allows it to continue on to the next task. If not, however, it goes back to the first while loop and displays the initial image once again and asks for all these other ranges. This initial while loop that we had is all the way up here. This was the z equals 1 while loop that we initially had, and then it shows the initial image all the way again and asks all the same stuff to make sure that the user is in fact putting in the correct values for the minimum and maximum x and y values. If, however, they do not put in a valid input, if they put in some other letter or a number, then it will display entry invalid for anything else, and then it will ask once again, is it a complete bacterium or not? Then, after all this is displayed, we go on, and in the next task, actually, it's going to estimate an ellipse of this one bacterium.
Hello, my name is Sisuni Wuttiwongyotin. I'm gonna to describe, starting from task 5, how our team of our course is run. Start from task 5. The first things that I do is I'm trying to use the function h in order to find the bacteria boundary, and it can show right here in the figure T by use this function h, and use Sobel function inside here to find, which is one method to find the boundary. And this command I show the edge or boundary of the bacteria that I use by the function s right here. And after that, I use the boundary of this bacteria edge in a matrix or array in order to use to find the parameter of this bacteria. And after that, I'm trying to find the maximum I'm trying to find the maximum value of x and maximum value of y in order to find the parameter by returning first here I'm set the x max equal to the max column, because of in the image is will start the x is row and the y is column, so I'm return the column as x and find the x max here, and this line I find the minimum x is which is equal to the minimum of the x column, and y max is equal to the max of the row. And for the x max, x min, and y max, y min, I can find the center of this bacteria by divided is by 2 in this command. So I can by use x max minus x min and divided it by 2. Also I can find the y coordinates of the center by using y max minus y min and divided by 2 also. And after that, after I have the center point here, I can find the each line is radius of this bacteria, because of now we have the coordinate here every point of this bacteria here, and now we know the center, so we can apply the trigonometric to find by using this command. So each line of the radius from the center to the body of this bacteria, we can use the square root of x every x from here minus with the x center and square it, and plus with the y of this boundary minus with the y center and square it. After that we square root it, we will get the every line from the center to the boundary. And after that we can find the semi-major axis of this bacteria, because of it is the largest distance from the center to this, and for the semi-minor axis is the minimum distance from center to the bacteria boundary here. So I can apply by use A equal to the max C and B equal to the minimum of the C also. So after that, for this line, after we know the parameter of this bacteria, we can find each area by using this equation pi times with A and B. And this line of course is gonna to find the ellipse angle by using trigonometric again. And here dx is the I can find from the different distance between x and the different distance between y, x, y, and can find the angle by use a tan equal. The angle is equal to a tan d by dx, which will return the degree, the angle in degree. And after that, this line show the I'm just trying to display how the bacteria parameter, which is A, will return the semi-major axis, and this line will print the semi-minor axis value of this bacteria, and also the bacteria area that we can calculate from the parameter. And this line will print out the angle that we can find from the course. And now this here, I'm going to plot the ellipsoid shape. After we found the parameter, we can plot it by using the ellipse 1 by input the center of the bacteria xc, yc, and we input this as an eccentric that we define before in this line. ECC equal to the access to ECC A, comma B. A is the major axis and B is minor axis in order to find the eccentrics of this bacteria. So, and we input it in here, and we have to input the bacteria angle that we already found it, and plot it by show in figure 4. And I'm gonna plot it by using the isolated bacteria that we already have and overlay it and show in figure 4 here. So the shape is look different because of the pixel here is have, because of the ellipsoid that we trying to find is estimating parameter and is smooth it and the shape is kind of smooth it from this bacteria pixel, but the area is equivalent together. So I will show the area again. Next, on task 6, now we are going to find the pixel or area of the isolated bacteria. First, declare find the size of the isolated bacteria by input in an array here in C1 and C2, and after that this line set the one white set the initial value for one white pix equal to 0 and one black pix equal to 0, and after that use for loop to loop through this array in order to find or count the number of pixels. For J equal to 1 to the R1 and for I equal 1 to C1, and if the isolated pixel of that bacteria I and J is equal to 0, it will return, it will keep the value and count it in here, and else if it found the value as 1, it will return and keep it in the one white pixel here. So for the black color is the value of the pixel black color is equal to 0 and end it. So this here you can find the pixel of this one isolated bacteria, and after that I print the bacteria area here that we count is from the pixel. And next, task 7. This task we are going to find the total number of the bacteria of the whole picture. The first line, this task I use another method to find the pixel of this picture by using sum of the whole picture equal to 0. So this is the black color that we gonna to count it, and all white is the total number of the white color pixel in the whole picture of the bacteria. So after that we will get the total number of pixel, and I'm apply by using the all of the pixel of the black color divided by the one bacteria pixel that we already have in task 6 here. So we will get the number of the total bacteria, and this line F prints F in order to print the total number of in order to all black in order to show the how many pixels of the whole picture that we have, and after that this line F print F the total number of the bacteria with counting by pixel. And this line error is the command line in order to show the how of the percentage error between the ellipsoid area that we calculated from the parameter that we find from the task file, comparing to the one bacteria area that we count it from the pixel. And now this line I'm going to print the error, how many percentage that we have from the ellipsoid, from comparing from the ellipsoid parameter that we calculate and from the pixel that we have in the one bacteria.
Okay, so now an example of how our code works. There are slight differences in how it works on different computers, just to the differences in MATLAB and how it operates on different processors and operating systems, but this is a good representative idea of how the code works. So you can see we have the code up here, and let's begin. So you can see that we have all the whose attributes here, as we did not comment that out in this version. You can see the size of the image and the how large the matrices are and the actual physical size of the data in the image. So then here is the converted image to black and white. And you can see that we want to find a range from where there's a single bacterium, so the minimum X value. I'm going to choose this bacterium. So it looks like that the minimum is 75, maximum is 100, and then 125 to 175 for the Y. So let's try that. Okay, so we have an isolated bacterium, and there is most definitely only one bacterium in there. So I will say yes, there is only one complete bacterium displayed. And here you can see that we have a bacterium and an estimated ellipse. And by taking the pixels in this one single bacterium and dividing by the total, you can see that here more specifically is the outline of the shape of the bacteria. Then it says that the percent error is fairly small. And then the total number of bacteria looks like about 89 or 90 bacteria, which we can confirm is correct as we have counted. And so there we go, that's it. I'm Adam Simcoe. I was partners with Natasha and Srisuni, and this was our final project for Bacteria Engineering 6, Section A04, and that's it. Thank you.